In this lecture, we'll continue our discussion on the Rankine cycle, and in this lecture, we'll look at the effect of pressure and temperature on the Rankine cycle. Then we'll consider the Rankine cycle with reheat, and finally, we'll look at the regenerative Rankine cycle. Before we discuss these topics, let us just look at the solution of the problem that I posed towards the end of the previous lecture. So the problem was that if we have a basic Rankine cycle with the boiler pressure of 2 megapascal and condenser pressure of 10 kilopascal, then what is the efficiency? And to look at this, consider on this TS diagram the cycle shown in the yellow color. The first step in performing the thermodynamic analysis of this Rankine cycle is to identify the various states and the enthalpies at these states. And once these states have been identified and the enthalpy is known at various states 1, 2, 3 and 4, then we can calculate the efficiency easily. So let's just identify the various states. At state 1, the substance, that is water, is at saturated liquid state, so the quality is 0 and we know the pressure, that is 10 kilopascal. So looking at the steam tables, or you can look at the software which give the properties of water, and then you will get that enthalpy at state 1 is this 191.8 kilojoules per kg. Next, we want to find enthalpy at state 2. So as we have seen in the last lecture, for the case that S2 is equal to S1, the enthalpy of this compressed liquid state at 2 can be found using this equation, and we get the value 193.8 kilojoules per kg. Next, we want to find the enthalpy at state 3. At this state, the water is at saturated vapor, so the quality is 1, and we know the pressure, that is the boiler pressure, is 2 megapascal. So looking at the property tables, we can get the enthalpy at state 3, which is this. Next, we need to find the enthalpy at state 4, but at state 4 only we know this pressure, that is 10 kilopascal. But note that the process 3 to 4 is isentropic. So what we do is we first find the specific entropy at state 3, because we know the quality is 1 and we know the pressure, that is 2 megapascal. So we get entropy of the saturated vapor. And because the process 3 to 4 is isentropic, the entropy at state 4 is equal to entropy at state 3. So knowing entropy at state 4, that is the specific entropy and the pressure, from the property tables, we get the quality at state 4. And once the quality is known, we get the enthalpy at state 4. And the enthalpy at state 4 is this. So now we know enthalpies at all these important states, that are the inlet and the exit states of the various components of the cycle, such as the boiler, the turbine, condenser and the pump. And now we can look at the efficiency. So efficiency is given by this expression. Essentially what this is, 1 minus the heat that is rejected. So heat that is rejected is H4 minus H1, and this is the heat that is absorbed per unit mass of the substance, and the heat that is absorbed in the boiler, that is H3 minus H2. And we know all the enthalpies, and now we can calculate the efficiency. It turns out to be 0.303, that is 30.3%. Now if we consider a Rankine cycle with same boiler and condenser pressures, but we consider superheating to 300 degrees Celsius, so then the inlet condition for the turbine would be this state 3 prime. and to determine this state, we already know that its temperature is 300 degrees Celsius and the pressure is 2 megapascal. So knowing these two properties, we can find the specific enthalpy and specific entropy from the property tables. And again, using the same procedure that the process 3' to 4' is isentropic, we know the specific entropy at state 4', and we also know the pressure is equal to the condenser pressure, that is 10 kilopascals. So all other properties are known, and here H4 prime is given by this value 2143.6 kilojoules per kg. So once we know all these states and enthalpy at all these states, we can calculate the efficiency, and it comes out to be 31% for this Rankine cycle with superheat. So what we see is that the Rankine cycle with superheat has higher efficiency than the basic Rankine cycle. And let's also compare this efficiency with efficiency of a Carnot cycle between same pressures, that is the boiler pressure and the condenser pressure. So the saturation temperature corresponding to this vaporization process in the boiler is 485.53 Kelvin, and for the condenser it is 318.96 Kelvin, because we know the saturation pressures, so the saturation temperatures are dependent upon the saturation pressures and they can be found from the property tables. So these are the temperatures, so the efficiency of the Carnot engine would be and this comes out to be 34.3%. So as expected, the Carnot efficiency is higher than the efficiency of the basic Rankine cycle and the Rankine cycle with superheat. So now we can look at the effect of pressure and temperature on the Rankine cycle, and in particular we look at the effect on the efficiency of the Rankine cycle. As noted in the previous lecture, the efficiency of the Rankine cycle can be thought of as that of a Carnot cycle with average temperatures at which heat is added and removed. Keeping this in mind, now we can consider the first case where we look at the effect of condenser pressure on the efficiency. So let's look at this basic Rankine cycle on a TS diagram, and now let's say that we reduce the condenser pressure. So initially, let's say the condenser pressure for this cycle was P4, and now we consider a new cycle where the condenser pressure is lower. So we know that the isobars corresponding to lower pressures will lie below. So this is an isobar at lower pressure P4 prime, and then we'll have this modification to the cycle if we reduce the condenser pressure, because the boiler pressure we are keeping to be the same, that is pressure P3. So what we see is that as we reduce the pressure, clearly the temperature at which heat is being rejected goes down. So if the temperature at which heat is rejected decreases, then the efficiency of the cycle will also increase. Another way to think about this is that when the exhaust pressure is reduced from P4 to P4 prime, then the area enclosed within this cycle will increase by this much amount. That is shown in this shaded region. Recall that the area enclosed within the cycle is the work done by the heat engine, and this area that is shown in this shaded region is the additional work that is now being done due to reduction in the pressure. Whereas if we look at the amount of heat that is added, the increase in the amount of heat that is added is this area under 2 prime to 2 states. This is the increase in the heat added to the working substance if we reduce the pressure, and this area is the increase in work that is done upon reducing the condenser pressure. So these two areas are roughly equal. Therefore, if we now consider the efficiency, so if we consider the efficiency of the original cycle that was in yellow color, that is, let's say, the net work output over the heat that is absorbed per unit mass of the working substance. Now, if we look at a new cycle, that is this cycle which goes from 1 prime, 2 prime, 3 and 4 prime, then let's say that the work that is delivered has increased by a certain amount. Let's say that is W net plus delta W, and looking at these areas, we've concluded that the heat that is absorbed also increases roughly by that much amount. So let's call that as QH plus delta W. So if we look at this expression, this can be written as, so clearly this part is our efficiency of the cycle 1, 2, 3, 4 that is shown in the yellow color, whereas this part, if you see, because the network is less than the heat that is absorbed, you can confirm that this ratio is greater than 1. Therefore, what we have is that the new cycle having lower condenser pressure has higher thermal efficiency. Therefore, the thermal efficiency increases by lowering the condenser pressure or the exhaust pressure of the turbine. However, when we reduce the exhaust pressure of the turbine or the condenser pressure, then we see that the quality at state 4 prime will be less than the quality of steam at state 4, that is this. That means at lower condenser pressure, there would be more moisture in the low pressure stages of the turbine when the exhaust pressure of the turbine is low. And as we've discussed earlier, this is not a desirable situation. So a better way to increase the efficiency of the Rankine cycle is by superheating. So as shown on this T versus S diagram, when we have this superheating, that is, we now superheat the vapor from state 3 to 3 prime, then the increase in the work output will be this much, shown in the red color, compared with the basic Rankine cycle shown in the yellow color. Whereas the increase in the heat that is absorbed by the cycle is this area under this curve 3 to 3 prime. So this is the increase in heat that is absorbed due to superheating. So if we consider the ratio of the areas, that is this area that corresponds to the net work done by the basic Rankine cycle by the heat that is absorbed by the basic Rankine cycle that is shown in this blue shaded region, then the ratio of the increase in work, that is the red area divided by the green area, that ratio is higher than the ratio of this area enclosed by the basic Rankine cycle by the heat that is absorbed by the basic Rankine cycle. So what that means is that upon superheating, the efficiency increases because now the relative increase in work is more than the increase in the heat that is required for superheating, and hence the efficiency also increases due to superheating. And obviously, as we have seen earlier also, superheating results in an increase in the average temperature at which heat is absorbed, and hence the efficiency increases. And we have also seen this through an example in the beginning of this lecture, that superheating results in increase in the efficiency. Next, let's look at how we can increase the efficiency of the Rankine cycle by increasing the boiler pressure, or the pressure at which the heat is being added. Consider a Rankine cycle with superheat that is shown in this yellow color. So this heat is added at pressure P3, and P3 is lower pressure than this pressure P3 prime. So if we increase the boiler pressure while we keep the temperature at which the vapor is superheated to be same, because that is limited by the available materials by which the equipment is constructed, therefore the maximum temperature will keep fixed but the pressure will increase. So what we see is that if we change the pressure from P3 to P3 prime, then there is a reduction in the work that is delivered, and that reduction is shown in this red color. But there's also increase in the work that is delivered, and that's shown in the blue color. So the decrease in the network is roughly equal to the increase in the work due to increase in pressure, because the blue shaded area and the red shaded area are roughly equal. Therefore, the net work remains almost unchanged. However, if we look at the amount of heat that is rejected, the change in pressure from P3 to P3 prime results in a decrease in the heat that is rejected, and that's because this amount of heat that is shown by this area is not rejected by the Rankine cycle shown in the green color. Therefore, we have the same amount of work output with less heat rejection. Therefore, the efficiency increases. This is consistent with the fact that the average temperature at which heat is absorbed at higher pressure increases when we increase the boiler pressure. Again, in this particular case, what we see is that when we increase the boiler pressure, the quality at the turbine exit decreases. So from here we can see that the quality at state 4 prime is less than the quality at state 4, which is undesirable. To summarize, what we've seen is that the thermal efficiency of the Rankine cycle increases if we decrease the exhaust pressure of the turbine. It increases if we increase the boiler pressure, that is the maximum pressure. The efficiency also increases by superheating. However, only superheating results in an increase in the quality of steam leaving the turbine, whereas if we reduce the exhaust pressure of the turbine, or if we increase this boiler pressure, then the quality of the steam exiting the turbine will decrease, and that is not desirable. So we have seen that the efficiency of the Rankine cycle is increased by an increase in pressure during heat addition. However, increase in pressure, as we have seen, is accompanied by increase in the moisture content of the steam in the low pressure end of the turbine. And this drawback can be addressed by this Rankine cycle with the reheat or the reheat cycle. In this figure, we have shown the schematic illustration of this cycle, and we've also plotted this on a TS diagram. So what we mean by reheat is that in this cycle, if you look at this diagram, so it resembles the basic Rankine cycle with superheat, and the difference is that we have now two turbines. One is the high pressure turbine and other is a low pressure turbine. So once we have superheated the steam to state 3, as in the usual Rankine cycle with superheat, first the steam expands in the high pressure turbine and it goes to state 4, and it's not expanded completely to the condenser pressure, that is pressure over here P6, and instead what we do is that the exhaust of the high pressure turbine is again fed to the boiler as shown in this red colored line over here, and then the exhaust of the high pressure turbine is heated and we again have steam at a superheated vapor state at state 5, and that is fed to the low pressure turbine and expanded completely to the condenser pressure. So this step, that the exhaust of the high pressure turbine is heated again in the boiler and then fed to the low pressure turbine, is called the reheat step. So you can see that there is little change in the average temperature at which heat is added, and hence there is little gain in efficiency. However, the advantage of this cycle is that the quality of the steam at the lower end of the turbine, that is the low pressure turbine, increases, and that is the advantage of the reheat cycle. So clearly you can see that the quality at state 6 is very high. So this idea of reheating can be implemented more than once. So we can keep on doing this reheating steps multiple times, but it will also complicate the system. The modifications that we have discussed so far increase the efficiency of the Rankine cycle compared with the basic Rankine cycle. However, the efficiency is still less than the Carnot efficiency. The scheme for realizing Carnot efficiency while retaining features of the Rankine cycle can be attained by a process called regenerative heating, and the resulting cycle is called the regenerative cycle or the regenerative Rankine cycle. So this regenerative cycle, in particular the ideal regenerative cycle, is shown over here. For this discussion, we'll just consider the Rankine cycle without superheat. So what happens in this ideal regenerative cycle is that to increase the average temperature at which heat is added, this liquid, that is from state 2 to 2 prime, is not heated in the boiler. Instead, if you look at this diagram over here, so the condensate that is at state 1 is pumped to state 2 by this pump, which consumes work, and this compressed liquid that is at state 2 is now not fed to the boiler, but instead it is circulated through the turbine and it flows in the direction opposite to that of the vapor in the turbine. So the heat is transferred in the turbine from vapor to the liquid, and for the moment we assume that this is done by having vapor that has temperature that is infinitesimally higher than that of the liquid. Therefore, at exit from this turbine, the state of the liquid is the saturated liquid at the boiler pressure, that is this state 2 prime, and thereafter it is heated in the boiler and then expanded through the turbine. But because this much amount of heat that is under this curve 2 to 2 prime is now added to the liquid by the turbine, the expansion process in the turbine is shown by this curve, that is 3 to 4. So point to note over here is that this area is exactly same as this area, because this is the amount of heat that is lost from the vapor over here, and this is the amount of heat that is gained by the liquid in the turbine. And this is the heat that is lost by the vapor in the red shaded area. So the net effect is that because these areas are the same, so this area is exactly equal to this particular area. In other words, if you consider the area enclosed by this curve, let's show in the blue color, is exactly same as the area enclosed by this Carnot cycle, that is shown in the yellow color over here. That is, the work output of this ideal regenerative cycle is exactly equal to that of the Carnot cycle, and the heat that is added during the step 2' to 3 in the boiler is also same as that for the Carnot cycle. Therefore, the efficiency of this ideal regenerative cycle is exactly same as that of the Carnot cycle. But the practical realization of a turbine with heat transfer, such as that shown over here, along with the fact that the quality of the steam exiting the turbine is very low, and therefore the practical realization of such a turbine is not possible. Therefore, this is again an ideal cycle. It's not easy to practically realize this. So the practically realizable option is to modify this regenerative cycle by keeping the turbine adiabatic. Instead of having heat transfer within the turbine remains adiabatic, but to heat the water, some of the steam from the turbine that is at state 6 after partial expansion is extracted from the turbine, and that fraction of steam is used to heat the water in the liquid phase. So the condensate at state 1 is again pumped to some intermediate pressure that is equal to the pressure at which this steam is extracted from the turbine, that is at state 6. And then these streams of extracted steam and the fluid at state 2 are mixed in this device called the feed water heater, and the resulting fluid is at the saturated liquid state at a pressure that is between the condenser pressure and the boiler pressure, and thereafter it is pumped to a higher pressure and fed into the boiler, and the vapor exiting the boiler is expanded in this adiabatic turbine to do work. So the fraction of the steam that is extracted at state 6 is just sufficient to cause the liquid that is exiting the feed water heater, that is at state 3, shown also on the TS diagram, to be at a saturated liquid state. So this practical regenerative cycle is shown on this TS diagram. And what we see is that the average temperature at which heat is added increases because the heat in the boiler is now being added from state 4 to 5, and therefore the average temperature of heat addition increases, and correspondingly the efficiency also increases. Next, let us calculate what is the fraction of steam that we must extract at state 6 from this turbine, so that upon mixing with this liquid at state 2, the resulting liquid at state 3 is a saturated liquid, that is, quality at state 3 is 0. So to obtain this fraction of steam that we need to extract, let's consider a control volume around the feed water heater. So if we consider this control volume in blue color, first we'll apply the principle of conservation of mass. So the inlet to this feed water heater is from 2 and 6, so m dot 2 plus m dot 6 is equal to the mass flow rate at the exit, that is m dot 3 for the feed water heater. Now let's say that at the inlet of the turbine the mass flow rate was m dot 5, and let's say that the fraction of steam that is extracted midway during the expansion process at state 6 is given by y. Therefore m dot 6 is equal to y times m dot 5. So this is y times m dot 5, and the remaining goes through the exit 7, that is m dot 7 would be equal to 1 minus y times m dot 5, and what goes into the condenser at steady state comes out, so therefore m dot 1 is equal to m dot 7, and that is again 1 minus y times m dot 5, and also m dot 1 is equal to m dot 2 from this pump. Also note that m dot 3, that is this mass flow rate through this pump over here and the boiler, is also equal to m dot 5. So next note that if we apply the conservation of energy or the first law to the control volume shown in blue color over here, what we would get is there's no work that is done and also no external heat that is transferred. So m dot 2 H2 plus m dot 6 H6 is equal to m dot 3 H3. Now what we can do is we can write m dot 2, m dot 6 and m dot 3 in terms of m dot 5. So if we do so, this is what we'll get. So m dot 2 is equal to 1 minus y times the mass flow rate into the turbine, that is m dot 5. Then m dot 6 is y times m dot 5, and m dot 3 is equal to m dot 5. So m dot 5 cancels out and we can solve for y, and we'll get y is equal to H3 minus H2 over H6 minus H2. So this is the maximum fraction we should take out at the pressure corresponding to state 6 from this turbine, so that when it is mixed with this liquid at state 2 in the feed water heater, we attain this state 3, that is a saturated liquid state. And note that on this cycle that is shown on this TS diagram, in this case one should just consider that this cycle just shows the state of the working substance. Because the mass flow rates through different components differ, one should be careful to interpret the area under the various parts in terms of the heat that is added or removed and the work that is done. So in this discussion of this practical regenerative Rankine cycle, we have assumed an open feed water heater in which steam and the liquid actually mix and result in the liquid at state 3. However, there are other types of feed water heaters also which are widely used, and those feed water heaters are called closed feed water heaters, where such mixing does not take place. So closed feed water heaters are essentially heat exchangers. So typically up to 6 regenerative heaters are used in an actual steam power plant. A typical thermal power plant employs simultaneous use of superheating, reheating, and regenerative heating. However, nuclear power plants, which also operate on the Rankine cycle, they usually do not have superheating and the reheating steps. And finally, note that the solar thermal and geothermal power plants are also based on the Rankine cycle. So this concludes our discussion on the Rankine cycle.